Hi, and welcome to the 10th tutorial video. This video introduces energy methods for dynamics with rotations. The first problem states, the lift truck has mass mt and mass center at g. Determine the largest upward acceleration of the spool of mass ms so that no reaction of the wheels on the ground exceeds F max. I find it easiest to split this problem and consider the spool and lift separately. We can draw free body diagrams for each body. Note that the lift has 4 wheels, so I'll write the reaction forces as 2Na for the left wheels and 2Nb for the right side wheels. Newton's second law for the spool gives us an expression that relates the reaction force at C to the acceleration. We write Newton's second law for the lift, noting that the lift does not accelerate, so the forces must balance out. Finally, we can sum the moments about point B and set that sum equal to 0 as well. At this point, we have 3 equations but 4 unknowns. We can fix this by setting the real reaction force to be equal to the maximum force. However, we're not sure whether the wheels on the left or the right will turn out to be the limiting factor. What we can do is simply choose one and see if our assumption is valid. Let's first try setting the reaction force at A to be equal to the maximum force, and see what we get as a result. We find that the acceleration is 3.96 meters per second squared. Furthermore, we find that the reaction force at B is 569.5 newtons, which is below the maximum allowable force. Therefore, this is the correct solution. If instead we found that the reaction force at B was over the allowable force, we would have to resolve the problem by assuming that NB was equal to F max. I also want to note that the problem gave us a dimension D, which described the height of point G. This dimension was not useful, so watch out for things like that in your practice problems and tests. The second problem states, the linkage consists of 2 rods AB and CD, each with weight W1 and a bar AD of weight W2. When theta equals 0, rod AB is rotating with angular velocity omega naught. If rod CD is subjected to a couple moment m, and bar AD is subjected to a horizontal force P as shown, determine omega AB at the instant that theta equals theta 1. This is the first problem which we have to examine using energy methods. Energy methods with rotating bodies is not much harder than the energy methods we looked at previously, and I'll quickly describe the differences. A rigid body can have translational kinetic energy, which is what we've considered before, but it can also have rotational kinetic energy. You add the two together to find the total kinetic energy of the body. Rotational kinetic energy is given by the expression 1/2 I omega squared, where I is the moment of inertia of the object, and omega is the rotational speed. If the object is rotating about a fixed point, it's best to use the fixed point as the reference for the moment of inertia. Otherwise, use the center of mass of the object. Just like how the work done by a force is equal to the force times the distance, the work done by a moment is equal to the moment times the angle. I'm using this fancy W for work since the problem already uses W for weight. We can use the same work energy equation as before. The force P and the moment m both contribute work into the system. We can then write the gravitational potential energy change for the 2 rods, as well as for the bar. Finally, we can write the changes in kinetic energy. The bar started out at a speed of A times omega naught, and ends at a speed of A times omega sub AB. The bar isn't rotating, so there's no rotational energy term. The red rods are purely rotating about their hinges, so we don't have to consider their translational kinetic energy if we measure their moment of inertia about the hinge point. The formula for the moment of inertia of a rod measured from one end is 1/3 times the mass times the length squared. With this information, we can write the change in kinetic energy of the rods. With this equation, we can find the rotation rate of the rods as 5.98 radians per second. Lastly, we have problem 3. It states, a chain that has a negligible mass is draped over the sprocket, which has a mass ms and a radius of gyration k0. If block A of mass ma is released from rest in the position s equals s1, determine the angular velocity of the sprocket at the instant s equals s2. Previously, we only dealt with massless pulleys, but now we have to consider the mass of the pulley. With the same work energy equation, we can write the terms for the change in gravitational potential of the block, and the change in kinetic energy of the block and the sprocket. The moment of inertia of the sprocket is equal to the mass times the radius of gyration squared. Next, the speed of the block and the rotational speed of the sprocket are related by the radius. This lets us find the rotational rate of the sprocket as 41.8 radians per second. That's it for today's video. As always, you can contact me at this email address if you have any comments or questions. Thanks for watching, and I'll see you in the next video.